David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, remember you can adjust the playback speed to make it faster or slower as you like. Second, you can pause the video at any point to catch up on your notes or jot down some questions. Third, you can turn on the captions so you can read my words on the screen. Today's lesson is going to cover how to use data to create a quadratic model of a projectile experiment. So I want to go over the overall steps just briefly, and then we'll dive into some of the algebra. So first off, this experiment, one of its intentions is to provide you with an example about how math arises naturally out of phenomena that we can observe. So our experiment, what we did in our class is we had a marble launcher and we launched it across the board so it made its arc and landed down there. We put a grid on the board so that we could take a look at the marble's path and be able to plot XY coordinates. We videoed that launch so we could play it back in slow motion, and then we played that video and we harvested data out of that. And so then that data got used to generate a model that turned out to be quadratic, and it turned out to tell us a whole lot of things about our experiment. Okay, so let's go through the steps. We got our data from a marble launch experiment. That was the experimental part of it. That's what we measured something in the real world. This was not a mathematically contrived thing designed to get a certain result. This was a natural phenomenon, something that happened, something that we made happen. We harvested height and distance data out of that because that's what our video could tell us. And then we calculated the time. We do need time for our equations, so we used the video's frame rate to figure out what the height was at various times. And this process is a little bit complicated and confusing, and it's different with different cameras and different frame rates and different computers analyzing that. So it was kind of a pain in the butt, and that part I'm not covering in this video. So you might need to get some help with that or figure it out on your own. But anyway, what we did is we calculated the time by harvesting that data out of the video. Then we used the data to find the equation. We did a quadratic regression with technology. And in my class, we used the TI-Nspire, the TI-84, or we just used Desmos, which is my tool of choice. It's just not always available to you when you're taking a test. So using your graphing calculator is a very important skill to have. Then what we did is we used the equation to find the x and y intercepts and to find the vertex. And that's fairly straightforward math, and I'm going to go over that with you in a minute. And then this was the hardest part, the algebra required to complete the square with the type of equation we get from this experiment. It's not easy. I'm going to show you an example with real data, and you're going to see how it goes. I would urge you to pay close attention, take good notes, because if you're in my class, you're going to have to do one of those on our unit test. Okay. Finally, what we did is we took our results, our vertex form, our intercepts, our vertex, and our equation, and we related it back to the experiment. And so we could confirm that our calculated results matched the results of our experiment. And that let us take our experiment full circle, evaluate what we did, and put it in the proper context. Action. Okay, to gather our data, we did this in a kind of a low-tech way. Our first thing is we used a ruler or a yardstick, and we marked this grid on the whiteboard. So we made a grid that had 10 centimeter squares. And it took a little while, and they weren't perfect, but the results from the experiment were quite good, so it was good enough for our purposes. So what we did is we made this grid, we labeled it, so these markings would be on the video, and then what we did is we positioned the launcher somewhere over here, and we filmed the path of the marble. So I'm going to sort of draw a path that it could have been. It might have gone like this. In some cases, people figured out how to make it go up pretty high. Doesn't matter. So that might be the marble's path. So we videoed it, and in the video, the marble goes, bonk. Okay? So, and just to know, if you use a whole whiteboard, you might end up with maybe 200 centimeters and certainly more up here. But I've scaled this down for the purpose of this little lesson. Okay, so then we took the video of that and we played it back on the computer in a frame by frame way. And so what we did is we we focused in on certain points along the way. And we gathered about 20 or 25. I'm just going to put a few here. But what we did is we paused the video at each point and then read the position off the graph. So for example, this point might be 5 centimeters and 18. So that would be 518. And then this point, looks like that's right on the 20. So this point might be, let's say 1420, and so on. And so we just got all these data points off of our graph. When we harvested our height and our distance data, we also counted frames so we could figure out some time information. And then we put it in a big table. So I'm going to show you that over here. So we always put time first. Time is our independent variable. It's what causes the measurements that we get. We pick a time, and that's going to determine what height and what distance we record. So in my class, one of the ways that people got time was that they figured out that each frame was a 30th of a second. So this might be the first frame, and they had 5 and 18, so they put 1/30th. This might have been the 5th frame, so they had 14 and 20, and then maybe this one was the 12th frame, 30 and 24. So they counted 4 frames to here, and then they counted 7 frames to there. And that's kind of what I'm trying to show on this graph, where we went 5, 14, and then 30, and we climbed up from whatever that was, 18 to 20, and then maybe to 24. So that's the process. And when we got done with that, we had a list of about 20 data points with time, height, and distance. And then we made our equation. Okay, I didn't put the step number on that last board, so scoot up in your notes and just write 1, gather data, over before you put that grid in there and showed what we did with gathering our data. This is step 2, finding equations. And I'm going to put, it's plural because we actually found 3 different equations. So I'm going to demonstrate with the first equation, which was just height versus distance, but it's the same process for height versus time and distance versus time. So put all that data into the technology, TI-84, TI-Nspire, or Desmos, or there's a whole bunch of other technology things that will do the same thing for you. But you just put it in the calculator or in the technology, and you tell it, I want a quadratic regression on that data, and it will give you back an A value, a B value, and a C value. And you remember the standard form of a quadratic equation is ax squared plus bx plus c. So what it's telling you is for this equation, our a, which is the one that's on the squared term, is minus 0.0056. Our b is 0.466, and our c is 22.4. So it has figured out the equation for you. Sometimes technology will actually show you the equation. Other times they just tell you the a, b, and c. And it's up to you to turn that into an equation. Now I want to talk about that a little bit. We like to write it in function notation, and we use certain variables. So height as a function of time is equal to minus 0.0056 times squared. So I'm not using x. I could put x there and there and there, and that'd be fine. But we're talking about time, so let's use t for our variable. So you can see I've just substituted in my a, b, and c in this format, but using t for time instead of x. And there's my equation. So that's pretty cool. This equation arose naturally out of the data that we collected. All right, let's find the vertex. And there's a quick and easy way to do that without completing the square. We are going to do completing the square in a minute, but we can find the vertex without going through all that math. So check this out. The x-coordinate of the vertex is given by this little tiny formula. You just take your b, change the sign of it, and divide it by twice your a term. So pause the video, do a plug-in step, and if you're feeling bold, get out your calculator and find the answer to that. Okay, let's see how you did. My plug-in step, minus 0.466, because it's minus b. b is positive, but I have to minus, change the sign, and then it's 2 times minus 0.0056. When I did this math on my calculator, I got 41.6. So that's the x-coordinate of the vertex. Now, to get the y-coordinate, you take the x-coordinate and you put it into your equation, and you do that math, and that gives you the y-coordinate. So pause the video and do your plug-in step for that. Okay, here's my plug-in step. I just put in 41.6 wherever t is in this equation. So h of 41.6 is minus 0.0056 times 41.6 squared, right there, plus this times 41.6. Finally, this is just the regular thing, comes back down to 22.4. Not sure why I have that parenthesis there. It's not necessary. Okay, so the only tricky part about this is you need to make sure that you square 41.6 before you multiply it by minus 0.0056. So make sure you do that and come back and give me the y-coordinate of the vertex, and then I want you to write the coordinates of the vertex as a coordinate point. Okay, when I do my number crunching, my plug and chug on this deal here, I get 32.1. So that tells us the vertex x-coordinate from here, y-coordinate from here is 41.6, 32.1. Somehow I lost the footage of the prompt setting up the next step, which is to find the intercepts. So that's why I'm dressed differently. It's just that it's a day later from when I shot the other one. So here's the prompt. Find intercepts and vertex. So first, we're going to focus on the intercepts. I repeated our equation here with our A's and our B's and our C's. And there's two methods. One is super easy. If you know how to use your graphing calculator, this is definitely the best way to do that. You can just graph your equation and find the intercepts. In your calculator, these are probably more often called finding the zeros, because that's when the y value is 0. It's when it crosses the x-axis. So you can do that. If that's your preferred method, I would say pause the video right now, graph the function, and see if you can come up with the intercepts. The second way is using the quadratic formula. This is where you plug A, B, and C into the formula and you solve it. Now, just to remember, our formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, if you're in my class, you want to make sure this is on your cheat sheet for our unit test, because I will prompt you at some point to use the quadratic formula to solve. If you have your graphing calculator, you can still graph it to check your answer, but you're going to have to show me steps using this to solve for the intercepts. So pause the video, pick your preferred method, and come right back. Okay, let's see what you got. For me, I got minus 34.10 and 117.30. Now remember, in this case, the y-coordinates are 0 because the x-intercepts are where it crosses the x-axis, and y does equal 0 at that point. Okay, I added a 3b step. It wasn't on the overview that we started the video with, but it's an important step, and we definitely did this in class. And that's make a graph. We really want to make a graph because that shows us the relationships that we're exploring here. So I summarized the important data that we're going to need for our graph, our x-intercepts from before, our y-intercept here, need my closing parenthesis, and then finally our vertex. This is the information we're going to need to sketch a nice graph. I put my axes on here. Now we have distance and we have height. And we're going to put it in centimeters for both of these. Now comes the part what people struggle with. We need to scale the axes so that the graph uses up the space and isn't too small or too big. So here's what I do. X-axis, it needs to contain minus 34.1 and 117.3. So I'm just going to go ahead and put 117.3, and then minus 34.1 is probably going to be about here. Okay? And I don't need to put a million tick marks on there. I just put the points that matter. The y-intercept, that's 0, 22.4. So I can just write 22 point, actually that's going to get in the way. So let's scoot this over and do 22.4 there. Okay? So now I have those, and then I need to put my vertex in there. So 32 is probably about a third of the way to here. It's somewhere right about there. and 41 is going to be almost twice as much. So that's a rough estimate. For this graph, that's totally fine. And now I need to sketch my parabola. So what I'm going to do is I'm going to recognize A, that there was no negative on the distance. We launched it from a height. So it's going to go something like that, okay? And that's a graph of our parabola. But this graph is made from the equation, not from the data. It should look a lot like your data, but this one is made from the equation that we derived from the data. Kind of interesting. And then let's talk about this. I'm going to dash it in because there's no negative. So even though this is mathematically the intercept for the function, it doesn't have a basis in the reality of our experiment. So we really don't need it. So I put it in as a dash. Now, check this out. It shows what happens. It tells the story of the marble. The marble is going up as distance increases. It reaches its peak, and now it starts going down. While distance keeps increasing the whole time, distance is always increasing, but height goes up and then it goes down. And this is due to the force of gravity, which we all know. So it's not surprising that it ends up going down. Also, remember our A term is negative. That means it's a downward facing parabola. And guess what? That's what we got. Okay, buckle your seatbelts. We're going to do the most intensive algebra on our equation. We're going to get to vertex form by completing the square. Now, there are other ways to get there, including from your graph, but this algebra is important. It's also part of algebra 2 to be able to complete the square. This one's messy because it has lots of decimals, but I'm going to show you a way to make this work a little bit more easily. So, and I'm going to explain this one quite a bit as we go. Here's our function, h of t, 0.0056t squared, 0.466t plus 22.4. So the completing the square process requires that the quadratic term, the squared term, not have a coefficient in front of it. There can't be a coefficient. So what we're going to do is we're going to factor it out. We're going to divide it out of each term. So what I'll get is I'll get minus 0.0056 parentheses t squared, because I just divided this term by minus 0.0056, and that gave us a t squared. But I can't do that to this without doing it to each other term. So I have to divide this by 0.0056 and divide that by 0.0056 to get the two terms that go inside this parentheses. So let me go do that and I'll be right back. Okay, I got a really interesting result here, so that's kind of cool. It's not guaranteed to come out this way, but it did. So I factored it out of the t squared. I divided 0.466 by this, and I got minus 83.2. Because there's a lot of these, it's smaller than that. So there's a lot of these in there, so that's not surprising. That got bigger. And the same thing with 22.4. There's 4,000 0.0056s in 22.4, so we got 4,000 out there. Now, I rounded all of these numbers, so the fact that we got 4,000 even is just sort of a lucky chance due to my rounding. But it's kind of cool. You wouldn't expect that with all these messy decimals up there. Okay, so now we're going to do one of the key steps of completing the square. We have to figure out what this is. Actually, what this is. b over 2 squared. This is one of the key steps in completing the square. We have to take the b term, the coefficient, and divide it by 2 and then square it. So pause the video and do that. Okay, when I do that, here's my plug-in step. B minus 83.2 over 2 squared. I get 1731. What the next step is, and these are just steps you have to remember. If you're in my class and you have a cheat sheet, you want an example of one of these problems for our test so that you know what to do. So check this out. I'm adding and subtracting b over 2 squared. Seems weird, but I'm going to show you why in just a second. So my b over 2 squared is 1731. So I'm keeping my parentheses around this section because that's what I'm manipulating right here. So I have my t squared minus 83.2 plus b over 2 squared minus b over 2 squared. And then I bring my minus 4,000. So I haven't changed anything. I'm adding and subtracting the same number. So this much expanded piece is the same as this one. I haven't changed it, but it's going to allow me to do a nice trick. Because of the way we did that, this becomes a perfect square. And so what that lets us do is factor this in an interesting way. So watch this. We end up with negative 0.0056 times t squared. Now this is minus b over 2. So what we do is we just do minus, so b over 2, so 83 divided in half is 41.6. So it's going to be minus 41.6 squared. So this is why we complete the square, because it makes this thing end up being really simple. And as you can see, here's a piece of vertex form. One more thing. This set of parentheses comes from these three terms. These set are different. So we actually have 2 parentheses there. I didn't bring it down, but that was a mistake. It needs to come down. And now I can combine these two together. We use this one to complete the square. So this minus 1731 goes with the minus 4000, and we're going to have minus 5731. And then finally our closing parentheses. Now this is starting to look pretty close to vertex form, but we're not quite there. So what else might we do? Pause the video and think about that for a minute. There's one more step that has to happen. It's a little tricky, but maybe you'll spot it. Okay, the minus 0.0056 applies to this term, but it also applies to this term. Because this is going to ultimately be the y-coordinate of the vertex, and there's no way it's negative 5,731. Our experiment didn't have any measures that were that many centimeters. That would be a long way down through the floor, and we know that didn't happen. So what we need to do is multiply minus 0.0056 times 5731 to get our true result. So pause the video and do just that. Okay, so that's what I get. I remove this outer set of parentheses. I'm not going to multiply into this because I have a squared, so I can't. I just bring that down. Whoops, lost my squared there. So I've got my minus 0.0056 times this, and now this ended up, when I multiplied this by this, they're both negative, so it goes positive, I get 32.1. Now pause the video for a minute and think about that result. Maybe look back over your notes. Tell me what you think. Okay, guess what? That's the same vertex we found before when we plugged things into the standard form equation. So our vertex is 41.6, change the sign of that one, and then 32.1. So, woohoo, pretty nice. We did a great job of that. Okay, step 5, relate it back to the real world. So I threw my graph up again just because I like to use that to talk about that relationship. And I want to point out, when we graphed this before, I told you where the vertex was, we talked about it, but I didn't label it on my graph, which is kind of an oversight. So you want to do that. So perhaps pause the video, go back to your graph, and we did put the point there, but we just didn't label it with the coordinates. So, okay. So this tells the story of the motion. As far as distance goes, it was always increasing distance as it traveled across the board. As far as height goes, it was not always increasing. It was slowing down in the increase till finally it stopped climbing, and then it started falling, going faster and faster and faster. So this tells the story of that marble. In fact, this graph is pretty much the path of the marble because we did distance versus height. So I want to point out 2 other graphs that we made. Okay, after we did all of this for distance versus height, then we started looking at time, which is actually more interesting as far as quadratic equations go. So then we used our time data to create 2 more equations, 2 more graphs, and answer a bunch more questions. So what I want to do here is just summarize the graphs and then summarize the real world applications of that, and then we'll be done. So here we go. Time versus height and time versus distance. I want you to pause the video, think real hard about the experiment we did, or if you weren't in the experiment, still, this is a good critical thinking step. Sketch what you think, however you think it might be, the line that represents the relationship between time and distance and time and height. Pause the video, think real hard, and come back. Okay, let's do these one at a time. Time versus height is the same because height still does the same thing, whether you're comparing it to time or whether you're comparing it to distance. Height still increases for a while until it hits a vertex on its parabolic path, and then it comes back down until it hits the ground. Okay, so that's very similar to mapping out distance versus time. Now think about distance versus height. I said that wrong. Okay, so now think real hard about time versus distance. What is that one going to look like? Pause the video and think real hard and come back. Okay, time versus different distance has a very different relationship. In our graph, in our original graph with distance versus height, the distance is always increasing. If the distance was decreasing, this curve has to come back towards the zero, and it never does that. It's always increasing. Also, when we graph the data, we got a straight line. So that tells us something about about the relationship between time and distance versus time and height. This is a quadratic relationship because gravity is a quadratic function. Gravity is what determines how the marble went up, but then finally went back down. The force of gravity is constant. It's always pulling on us. So that's why this graph is parabolic, downward facing, because gravity is a negative pull. It pulls us down. Now, distance versus time is different because distance was horizontal. So that component of the marble's flight was not affected by gravity. The horizontal part just kept on going horizontal. Even as it was rising and dropping, the horizontal part is constant. So it has a horizontal velocity that does not change. So that's why it's a straight line. The slope of the line is the rate. It's the amount of distance you get per unit time. So a faster marble shot out faster with more force would have a steeper slope because that's a higher rate, and a slower marble would have a shallower slope. This is a linear relationship. That makes lines. The rate doesn't change. When you go back to height, the rate of change in height is changing. Height is going up, the rate of change is positive, then at this point the rate of change is zero. It's not going up or down, and now the rate of change is negative. So quadratic relationship creates different things. Linear relationship creates straight lines. So that brings it all together. Now, the interesting thing is all these equations, all these graphs, all this analysis, all this algebra was generated from data. Now, this is probably not the way gravity's constant was discovered. It's probably not the way quadratic equations were discovered. Probably were discovered another way. But they could have been. They totally could have been. Someone could have done this experiment just because they were scientists back in whenever, and they measured the time and the distance, and they had a way of finding time. They did height and distance and so on and so forth. They got their data, and they started thinking about their data. They didn't have computers or calculators, but there's other ways to get the equation, and they could have done that. They could have discovered this relationship, and they could have built the whole branch of mathematics that we are currently exploring. So think about that for a while. I think it's pretty cool. Now that you've watched the video, take a moment to jot down any additional notes, some questions, or a quick summary of the lesson. You can also re-watch the portions of the video that were a little bit challenging for you. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.